Today's lesson, I'm going to introduce stereoisomerism. In today's lesson, I'm going to introduce stereoisomerism. Stereoisomers, they have their atoms linked in the same way or order, but they differ in the spatial arrangement of their atoms. Okay, so there are two categories that we need to learn. The first type is called geometrical isomerism. The second one is called enantiomerism or optical isomerism. So today we are going to focus on the first type, geometrical isomerism. So geometrical isomers, they are stereoisomers that have a different arrangement of their atoms in space due to the restricted rotation about a carbon-carbon double bond. Okay, so we use E or Z to distinguish the two isomers. And some of them can also be called as cis or trans isomers. So later we're going to learn the difference between these two naming systems. Okay, so here we got two examples. Okay, so these two molecules are called geometrical isomers. Okay, so in order to be geometrical isomers, it must fulfill two requirements. So first, they must contain carbon-carbon double bond. Okay, here I built some models that printed on your notes to explain this part. So first, let's take a look at these two molecules. Okay, this one represents the one that printed on the left hand side. The green ball represents the fluorine atom, and the rest of the white balls represent hydrogen atom. The two black balls represent the carbon atom. Okay, so this one we got the fluorine atom pointing towards us, and another hydrogen pointing inwards. Okay, on the right hand side we got this molecule which have one hydrogen atom pointing towards us, one hydrogen atom pointing inwards, and the fluorine atom is actually in the plane, so we just use a straight line to represent it. So just by looking at these two models right here, it seems like they are different molecules. However, because the carbon-carbon single bond can be rotated, so if we take the left-hand side molecule and rotate it 120 degrees, okay, now I put it down and you can compare the two models again. They become identical. Now take a look at the two examples on the right hand side. For this one, both molecule contains carbon-carbon double bonds, okay. This one the same, carbon-carbon double bond. But for the left hand side we got fluorine atoms pointing towards us. For this one we have one fluorine atom pointing towards us, one pointing upwards or inwards. Okay, and because the carbon-carbon double bond we cannot rotate it, okay, there is no way that I can rotate the right hand part and to change this green ball to the top part, okay. So they are actually different molecules, so they are called geometrical isomers. Okay, so because they differ in spatial arrangement of their atoms, and only the double bond would be restricted from rotation. So double bond is a key requirement for geometrical isomers. And second, they cannot have identical group attached to the same carbon atoms of double bond. So here again, I built the two models. So on the left hand side, okay, we have for the green balls, they represent the bromine atoms, and then we also got a methyl group attached to the double bond. And then we have this molecule, which is one on the right hand side. These two green balls represent the bromine atom, and then we got the methyl group attached here. So although we cannot rotate the double bond, but for this molecule we can simply flip it, okay, so turn it around, flip the molecule, and now they become identical. Okay, that's because they have identical atoms attached to this carbon on the double bond. Okay, so in order for they are identical molecules, so if you want it to be a geometrical isomer, it must have different groups attached to the double bond. And third, this is to describe what kind of properties geometrical isomers have. They have similar chemical properties but different physical properties. Again, later we're going to discuss the difference in physical properties in details. Okay, so the first part we are going to discuss is how to name our geometrical isomers. Okay, in order to name it as E or Z geometrical isomers, we have to determine the priority groups on both sides of the double bond. Okay, the rules is that we need to look at the atoms that directly attached to the carbon atoms of the double bond. Okay, and the atom which has the higher atomic number would have the higher priority. So here we got an example. So on the left hand side of the double bond, we have bromine and fluorine attached to the carbon. So bromine got atomic number 35, fluorine got atomic number 9. So bromine should have the higher priority in this case. So we can highlight it using red. Okay, and then on the right hand side we have chlorine and hydrogen. So hydrogen has atomic number 1, so of course chlorine gonna have higher atomic number than hydrogen, so we can highlight chlorine should have the higher priority. Okay, so now we have labeled the higher priority groups on both sides, and now you can see the two priority groups are on the same side of the double bond. Okay, both are on top of the double bond. So if in this case they are placed on the same side, okay, then we label it as Z isomer. Okay, if the priority atoms are on the opposite side, okay, and then we label it as E isomers. Okay, so remember Z is similar to same side, so that's Z. Okay, and for the other one, opposite side, then it should be labeled as E. Okay, so for this molecule, remember when we compare bromine with fluorine, bromine has higher priority, and if we compare chlorine with hydrogen, chlorine has higher priority. So the priority atoms are on the same side of the double bond, hence it's called Z isomer. Okay, so we place a prefix to the name of the molecule. And on the right hand side, again, bromine should have a higher priority, so we highlight it, and then chlorine should have higher priority, and we label it. Now we can see the two priority atoms are on different side of the double bond. Okay, different side. Hence, we name this molecule as E isomers. Okay, so that's how we assign Z or E to the molecule. And we also got a different naming system. Okay, so for some of the geometrical isomers, we can also name it as cis-trans isomers. So in order to be cis-trans isomers, it must have two of the substantive groups be the same. Okay, and you need to note that, remember the two groups, okay, must be placed on different side of the double bond. If it placed on the same side of the double bond, okay, I should make it clear. If the two same group are attached to the same carbon on the double bond, then it would not form any geometrical isomers. Okay, so it must be attached to different carbon of the double bond. Okay, and then if the same substituent groups are on different side, then we call it trans isomer. If the same substituent groups are on same side, then we call it a cis isomer. Okay, so here I use a different color to highlight the part that we use to determine whether it's cis or trans. Okay, so now for these two, let's practicing assigning the priority groups so that we can determine whether it's E or Z. Okay, so in order to find the higher priority groups, we have to look on both sides of the double bond. On the left-hand side, remember we compare the atomic number that directly attached to the carbon of the double bond. Yeah, so on the left-hand side, we have hydrogen and we also have carbon. So hydrogen, again, atomic number is 1. Carbon, atomic number is 6. So for the left-hand side, the higher atomic number should be assigned to the methyl group. So here I use number to represent the high priority atom. So similar to the left-hand side, because the methyl group got carbon that directly attached to the double bond, okay, so we should assign the higher priority to the methyl group. Now you can see the two priority groups are on the same side, so it's Z2-butene, or actually we should name it as Z-but2ene. Okay? Okay, for the one on the right hand side, again we divide it into two halves. On the left hand side, the methyl group should be assigned to the higher priority. On the right hand side, we give methyl group the higher priority. Now, the two priority atoms are on different side, opposite side, okay? So it should be named as E isomer. So E-but2ene, okay? E-but2ene. Okay, that's the first way we assign the two isomers, E or Z. Now let's use the rules that we just learned to assign whether it's cis or trans. So you can see on both sides of the double bond we got methyl group. Okay, so I use purple to highlight the position of the two methyl group. Okay, so for the molecule on the left hand side, the two methyl groups are on the same side of the double bond. Hence, it's called a cis isomer, so cis-but2ene. For the molecule on the right hand side, if I highlight the two methyl group, you can see the two methyl groups are on different side of the double bond. Hence, it's called a trans isomer, so trans-but2ene. Okay? Now, the next question gonna be, what's the difference between these two naming systems, okay? E and Z, cis and trans. Are they equivalent? Or can we substitute Z simply with cis in the name? Here we got more examples. Okay, so let's try to work it out for some of the molecule. Right, for the first molecule, again, let's try to assign whether it's E or Z first. So if we divide it into two halves, okay, on the left hand side, chlorine should be given a higher priority. On the right hand side, chlorine should be the priority atom. So here we got the priority atoms on opposite side. Hence we give the name E, okay, E,1,2-dichloroethane. Okay, and for the second molecule, chlorine got higher priority. So here, the two priority atoms are on the same side of the double bond. Hence, we call it an Z,1,2-dichloroethane. Okay, and then if we use cis and trans rules to assign these two molecules, on both sides of the double bond, we got a chlorine atom. For the first one, because the chlorine atoms are on the different side or opposite side of the double bond, so it's called a trans 1,2 dichloroethane. And for the molecule on the right hand side, the chlorine atom are on the same side of the double bond, hence we call it cis 1,2 dichloroethane. Okay, so if you use the same rules to examine the two examples below, you can also find that it's a trans-butene, but it can also be called as E-butene. And for cis-butene, it can also be called as Z-butene. So now, some of you may ask, can we simply or easily translate cis into an Z and trans into a E? Okay, trans into an E, cis into an Z. Does that always work for geometrical isomers? So let's look at one more example together. Okay, so here we got this example. Let's try to work out whether it's cis or trans, because it's quite straightforward to see. Okay, so on both sides of the double bond, we got a methyl group. Okay, so let's highlight it. So you can see the methyl group are on the same side of the double bond, hence we call it a cis isomer. And then let's try to work out the higher priority groups on both sides of the double bond. On the left hand side, okay, the higher priority should be given to the methyl group because carbon has a higher atomic number than hydrogen. On the right hand side, we need to compare the atom that directly attached to the carbon. So it should be bromine and carbon. So carbon has atomic number 6, bromine has atomic number 35. So the higher priority should be given to bromine. Okay, so now on the left hand side, the methyl group has higher priority. On the right hand side, bromine has higher priority. So the higher priority atoms are on different side of the double bond, hence we should name it as an E isomer. Okay, so here you can see it's a cis isomer, but it's also an E isomer. So it actually contradicts to the example that we have above. So for example, the butene example, cis isomer is also the Z isomer, but for the one that we have here, cis isomer, however, is E isomer. Okay, so it tells you that cis and trans or E and Z are determined by distinct criteria, so it's not interchangeable and it's completely different methods, so don't mix it up. Okay, if you are required to assign cis or trans, then follow the rules that we assign cis or trans. Okay, do not just translate E and Z into cis and trans. They are not equivalent at all. Now let's go through the checkpoint questions. You can pause a video here, attempt all questions, and then listen for explanation. Question 1. Consider the two molecules below. They are chain isomers, position isomers, geometrical isomers, or identical molecules. So first, if you take a look at the arrangement of the carbon chain, okay, both of them got 5 carbons in the longest carbon chain, so they are not chain isomer. And how about the position isomer? Okay, so the functional group for these two molecules is a CC double bond, and you can see the CC double bond is between the second carbon and the third carbon. Okay, second and the third carbon, so they are not position isomers. So we just need to focus on whether they are geometrical isomers or not. So if you pay attention to the molecule on the right hand side and study its structure carefully, you can find out that if you flip this molecule, okay, then it would actually turn into the molecule on the left hand side. Okay, so if you just flip this upside down, okay, then you will find that it's identical to the one we have on the left hand side. So they are identical molecules. So the correct answer should be D. Alright, next one. 4 possible structures of molecular formula C2H2CO2 are shown below. Which of the following is a pair of geometrical isomers? So remember, in order to be geometrical isomers, there should be no identical atoms or groups of atoms attached to the same carbon of the double bond. So if you take a look for molecule W, okay, there are identical atoms attached to the same carbon of the double bond, so it's not possible for W. Okay, and if you further take a look again for Z, it has identical molecules attached to the same carbon of the double bond, so it would not be the correct answer. So the correct answer should be X and Y, okay, so should be C. Next one, classify each compound as a cis isomer, a trans isomer, or neither. Okay, so in order to label it as cis or trans, we need to highlight the identical groups attached to the carbon-carbon double bond. So for the first molecule, it has ethyl groups attached to the different carbons of the double bond, and the 2 ethyl groups are on opposite sides, so we should name it as a trans isomer. For the second molecule, again, it got ethyl groups attached to the carbons, different carbons of the double bond, okay, and the 2 ethyl groups are on the same side of the double bond, so we should call it a cis isomer. Okay, how about the next one? Next one, you can see on the left hand side of the double bond for this carbon, it actually has 2 identical atoms attached to it. So it's neither a cis or trans isomer, and it's not even a geometrical isomer. Okay, so we just write neither. Then the next one. This one is a bit challenging. Okay, so draw the structure of the stereoisomers for each compound, label them cis and trans. If no cis and trans isomers exist, label them E or Z. Okay, let's work out the first example. First example, we have 2-bromo-pent-2-ene. Okay, if it's pent-2-ene, that means it should have 5 carbons in the longest carbon chain. Okay, and then the double bond should be between the carbon 2 and carbon 3. So let's draw the longest carbon chain. Okay, between 2 and 3, that means here we need to have a methyl group, and here we need to have an ethyl group. Okay, and then we need to put the bromine attached to the double bond onto it. So we got 2 bromo, that means the bromine is attached to the second carbon, so it should be this one. Okay, and then we just fill in the rest. It should have an hydrogen attached to it. For this molecule, you should notice that there is no identical groups or atoms that appears on both sides of the double bond. Okay, so it's not cis or trans isomer. Then we need to consider whether it's E or Z. So if we separate into 2 halves, on the left hand side we're going to compare bromine with carbon. Then bromine should have higher priority. On the right hand side we are comparing carbon with hydrogen, so carbon should have higher priority. Okay, so the priority groups of atoms are on the same side of the double bond, so we name it as Z isomer. Okay, and then we need to draw the other isomers of this molecule. So for the other isomer, again, we can, this time, we need to draw the E isomer. That means the priority group should be placed on opposite side. So we should put our ethyl group here. Okay, so when we assign the priority group, bromine as a priority group, and then the ethyl group is a priority group. Hence, we name this isomer as the E isomer. Okay, opposite side. And then for part B, we got hex 3-ene. For hex 3-ene, we have 6 carbons in the longest carbon chain, and because it's 3-ene, the double bond should be between third carbon and the fourth carbon. Okay, so we draw the carbon double bond, and it should have ethyl group attached to both sides. Okay, so double check 1, 2, 3, 4, 5, 6 carbons, and then we need to fill in the rest with hydrogen. Okay, so for this one, would you be able to find any identical groups of atoms on both sides of the double bond? The answer is yes, so we can highlight the ethyl group. So for the molecule I have drawn, the ethyl group is on the different side of the double bond, so opposite side. Hence, we should name it as a trans isomer. Okay, so for the other isomer, we need to draw the structure of the cis isomer. So cis isomer means that two ethyl groups should be placed on same side of the double bond. Okay, so that would be the cis isomer. Remember, when you draw this, the single bond, the carbon-carbon bond should be linked between carbon and carbon. Don't draw this line between carbon and the hydrogen. Okay? Let's move on to the next part. C. We have 1,1-dibromo butene. Again, we focus on butene part first. Butene, it means 4 carbons in the longest chain, and the double bond is between the second carbon and the third carbon. Okay, so we have methyl group attached to both sides of the double bond. Okay, and then we draw this molecule first. So that's butene. But then we need to deal with the 1,1-dibromo part. Okay, so here, this atom is the second carbon. Okay, so that will be the first carbon. And then because it's 1,1-dibromo, so we should substitute 2 of the hydrogen into the bromine here. Okay, so we should erase this part and put 2 bromine and 1 hydrogen to it. Okay, so for this one, again, we need to look for identical groups of atoms on both sides of the double bond, and you can see both of them have hydrogen directly attached to it. And for the isomer that I have drawn, the 2 hydrogen molecules are on the same side of the double bond. So we should name it as a cis isomer. So next we need to draw the trans isomer of this molecule. So the 2 hydrogen atoms should be placed on opposite side. Okay, and then we fill in the rest. So here, hydrogen are on opposite side, hence we call it a trans isomer. Okay. The last question. The following questions are about cis-1,2-dichloroethane and trans-1,2-dichloroethane. So it lists out the boiling point for the 2 molecules and also the melting point of the 2 molecules. Right, so as we can see, for the boiling point, the cis-1,2-dichloroethane has a higher boiling point. But for the melting point, the 6,12-dichloroethene actually has a lower melting point than the trans one. So what is the reason for that? Okay, let's see how we should answer this type of question. So first, compare the boiling point. The boiling point of a carbon compound depends on the strength of the intermolecular forces. So by now, you should, when it's asking you to compare boiling point or melting point, you should always have this sentence. Okay, and then we can further explain it in detail. So the 6,12-dichloroethane is a polar molecule. Okay, so remember the order that we compared. Remember the order that we compare the strength of intermolecular forces. The first one, can they form hydrogen bond or not? So for both of the molecules given, it will not be able to form hydrogen bond with the molecule itself. So we skip the first criteria. And the second criteria is that whether it's polar or not. So if we pay attention to this molecule, it got chlorine attached to the same side of the molecule, so it should have a dipole moment pointing upwards. Okay, so for the 6,12-dichloroethane is a polar molecule. But for the trans 1,2-dichloroethane, the dipole moment actually cancel out, one pointing upwards, one pointing downwards, so it cancel out. So for the trans 1,2-dichloroethane, it's a nonpolar molecule. So the polar molecule should have a stronger intermolecular forces. Hence, it requires more energy to break the stronger intermolecular forces. So let's try to fill in the blank here. 6,12-dichloroethane is polar, while trans 1,2-dichloroethane is nonpolar. Therefore, the strength of van der Waals forces between cis isomer is greater than that between the trans isomer. So more energy is required to break the van der Waals forces between cis isomer. Okay, so let's compare the melting point. The melting point is a little bit different to the boiling point. That's due to the molecular symmetry. Okay, so the key sentence you need to have here is the melting point of a carbon compound depends on the strength of intermolecular forces and the molecular symmetry. The van der Waals forces exist in both isomers and they are of comparable strengths. Okay, so and then the next sentence, molecule of the trans isomer has a more symmetrical structure. And thus some molecules can pack more compactly in the solid. So more heat is required to overcome the van der Waals forces between molecules of the trans isomer. Thus the melting point of the trans isomer is higher. Okay? And the last part, which one, cis or trans, is more soluble in water? So when we discuss the solubility in water, we need to consider whether it can form hydrogen bond or not. So for these two examples, both of them cannot form hydrogen bond. Then we need to consider whether we got a polar molecule or non-polar molecule. The polar molecule would be more soluble in water. So for this case, the cis isomer would be more soluble because it is polar.